Okay, so I mentioned three types of convergence. So it's not. So this section is not particularly important for this class. All you have to remember is that what you want to do kind of works. And but I want to make sure that we're not making any mistake. And since I'm trying to, give you a little bit of mathematical formalism, I want to make sure that we understand what we're doing from a mathematical standpoint. So those three types of convergence that appeared, there were two in the law of large number and one that showed up in the central limit theorem. The first that you saw in the law of large number is almost sure convergence for the strong law of large number and the convergence in probability. So those are, and the last one is the convergence in distribution that was in the central limit theorem. They're going from strong to weak in the sense that if you have this guy, then you have this guy, and then you have this guy. Okay? So those types of convergence, they just have to be different than what you know when you take limits from like sequences of number. What is the limit of 1 over n as n goes to infinity? That's basically what this thing is trying to do. But since you have a bunch of randomness of things that are moving around, you have to be a little more careful about how to do this. So the strongest one is essentially the one that says, let's just pretend that things happen as if it was a sequence of 1 over n. This is very close to what you know. This is the almost sure convergence. And essentially what it's saying is, basically, apart from something that happens with probability 0, I have the same convergence. I have the convergence for all deterministic aspects of it. So what does it mean? So here, this omega is typically the probability space that's underlying what you're doing. So for example, if you have, I don't know, you're flipping a coin and you're making decisions based on that. So you say, for example, I flip a coin and my random variable x is equal, or I flip 2 coins. Okay, I flip 2 coins. So my sample space is whatever the 4 possible realizations of those 2 coins. And I say, if I get 2 heads, my random variable x is equal to, or if I get twice the same result, my random variable x is equal to 3. And if I don't, my random variable is equal to 0. Okay? So that's one way to create a random variable from some probability space. What you want to have here is that for all possible realizations, if I have heads, heads, I want this to converge. If I have heads, tails, I want this to converge. All right, so here I gave you only one random variable. Now you could make a sequence of random variables. So if I have twice the same, my sequence of random variables is xn is equal to, say, 1 over n. And if I have two things that are different, my xn is equal to 1 minus 1 over n, for example. So I created 2 sequences. And now what I want is those things to converge no matter what the outcome actually is. Maybe apart from something which is of 0 probability, which will never happen in the so there's no outcome of 0 probability when you flip 2 coins. Okay? So this is basically as strong as it gets. You should think of it as being the same as the one that you're used to when you think of limits of sequences. One that's a little weaker, but it's nice because it's easy to play with. It's actually saying, I'm going to say that Tn converges to T if the probability that Tn minus T larger than epsilon goes to 0, no matter what epsilon you put in there. Okay, so I just want to say, okay, fix a distance at which those guys are, and measure the probability that they're farther from each other than this. Then no matter what distance you fix, I want this to go to 0. This is weaker, but this is in a way a very natural way to think about convergence of random variables. Right? The probability that they depart from each other by something is going to be going to 0 as n goes to infinity. Now, there's something very specific about convergence almost sure and convergence in probabilities, that those two random variables, Tn and T, for example, live on the same space. I can actually talk about their difference. Here, saying that Tn goes to T is the same as saying that Tn minus T goes to 0. Convergence in distribution is not of the same kind at all. It's a whole different animal. Convergence in distribution is really just telling me that the distribution of T converges to the distribution of, the distribution of Tn converges to the distribution of T. It tells me that this guy maybe converges to a Gaussian distribution. But when I write this Gaussian distribution never really exists. All I'm really saying is this is not a statement about the random variable itself and where it goes. It's just saying I'm going to measure something about this random variable. Maybe its distribution. I could have measured its mean, its variance, something. But I'm not saying that the random variable itself goes to something. I'm saying that an aspect of the random variable is convergent to something. And here I'm just saying that its distribution is converging to something. Okay? That's what, hence the word convergence in distribution. So the way you write it formally is by saying that for any bounded continuous functions, if you look at f of tn, then its expectation is going to converge to expectation of f of t. That's like, that's a formal mathematical way of doing it. What you're really trying to emulate here by those bounded continuous functions are indicator functions that take value, say, 1 on an interval and 0 elsewhere. Because now when I look at the expectation of indicator of, say, between a and b of tn, this is just the probability that tn is between a and b. And I want to say that it converges to the probability that t is between a and b. And that's what convergence in distribution means. It's just telling me that when I compute distributions for the one guy, I get the same values. Sorry, when I compute probabilities for the first guy, I get the same as the probabilities for the second guy, as n goes to infinity. Now, of course, the indicator function is not continuous, so you have to be a little careful about this. But essentially, this is what it means, and there's some extra conditions. OK, so those two things really tell you that my random variable is going to become this guy eventually. This is just telling me the distribution of this random variable is becoming the distribution of this guy eventually. So as I said, there's ordering in those guys. So if you have convergence almost surely, then you also have convergence in probability. And if you converge in probability, then you have convergence in distribution. OK? And the limits are the same. Things go well. OK? So as I said, the convergence in distribution that we're interested in is essentially this thing. So there's an extra regularity condition, which is continuity of the CDF of t, which is implied by the fact that, for example, I have a density. If t has a density, which will typically be the case for us because we're thinking of central limit theorem, so it's going to be a Gaussian. It does have a density. I showed it to you. And if you forgot, just pull out one of your Deutschmarks notes. And essentially, what it says is that now if I have Tn converging to T, then yes, I can compute probabilities of being in some interval. And essentially, from there, I can compute any probability I want. And it says that when I compute probabilities for Tn, they're going to converge to the same probabilities that I compute for T. And we have done that. We have done that, say, right here. When I said that I want to compute probabilities for this guy, but really I'm computing probabilities for that guy. That's exactly the statement right here. OK? So in a way, convergence in distribution is like weak. It's if you have this, it does not imply anything, whereas the other two give you something. Sure. But convergence in probability is all we need to start making those confidence statements and probabilities of deviations and things like this. So that's going to be something we work quite a bit with. Yeah, so let me just go quickly through the first one, for example. So if Tn converges in probability, then it also converges almost surely. Is this true or not? Well, first of all, did I say this? I did not say this. And it's actually because it's not true. And it's actually annoying to come up with an example where this actually fails. I mean, I can come up with one, but it's not supernatural. If you want to see one, come to office hours. I'll show you one. Typically, what people do is they use Burrell-Cantelli and just make some sort of opaque statement that says, well, Burrell-Cantelli tells us that it's not going to converge almost surely, but we can prove that it converges in probability. Here's another question. So now I have a random variable. This is capital Xn, sorry. Capital Xn has a Bernoulli distribution with parameter 1 over n. OK? So this is just a Bernoulli random variable. It takes value 0, 1, but the probability that it's 1 is just 1 over n. It goes down to 0, like 1 over n. And so you could actually compute a bunch of things. For example, the probability that xn bar, absolute value of xn, which for Bernoulli is equal to probability that xn exceeds epsilon. OK? So xn is a random variable that takes value 0, 1. So this thing is actually equal to the probability that xn exceeds epsilon. But if epsilon is between 0 and 1, let's say epsilon is between 0 and 1, that's what we write right here. Sorry. Then what is this probability? So you have a random variable. It can take either value 0 or value 1. When is it equal to? When is it larger than epsilon? Well, only when it's equal to 1. And we know that the probability it's equal to 1 is equal to 1 over n. It's a Bernoulli 1 over n. So this converges to 0 as n goes to infinity. So what is the answer to this question? Yes. Okay. So this converges in probability to the 0 random variable, which is deterministic. Okay, so just a quick question. So here we just concluded that 0 was the limit. And does it converge in distribution? Who says yes? Who says no? Has to be yes, because convergence in probability implies convergence in distribution. So if it converges in probability, it does converge in distribution. The nice thing about convergence in probability, it's actually easy to check, right? We just did it, and it's something we can actually compute. It's just the probability that some random variable is larger than something. So yes, it converges in distribution. What is the limit of the sequence expectation of cosine of xn as n goes to infinity? What can I say about the function cosine? What? It's between -1 and 1. So it's bounded. Is it continuous? Yes. So it's bounded and continuous. So I know that this thing, by definition of convergence and distribution, will converge to the expectation of cosine of 0, the limit of xn, which is 1. There you go. You could compute, and I recommend that you do this. I recommend that you actually check what the expectation of cosine of xn is, because, well, it's a Bernoulli random variable, right? This takes value cosine of, this random variable cosine of xn takes two values, cosine of 0 and cosine of 1, one with probability 1 over n, and one with probability 1 minus 1 over n. So compute it, and that will give you a little hint as to why you need those functions to be bounded. If they were not bounded, then you might not be able to conclude. Okay, so it's important that things are bounded.